Hi, Chris Kuzmal here. No BC calculus class would be complete without a definition of differentiation. This is supposed to be a review, but here we go. The formal definition of differentiation is that a function is f at x plus d minus f of x divided by d. That tells us something. That's sort of a slope of the function, approximately. But as d gets smaller and smaller, we get a more precise definition of the slope. And indeed, as d approaches zero, this becomes the derivative, the value of the derivative of the function f. So that formula, f of x plus d minus f of x divided by d, is your key. It's the linchpin to differentiation. But you know, division by zero is a problem. What if d is approaching zero and d is in the denominator here? I mean, what's the deal? That's the main issue. That's the whole purpose of introducing limits, because limits say, well, we're not actually going to have it be zero. We're just going to have it get arbitrarily close to zero. So to deal with that, what we try to do is avoid having to put that d in the denominator at all by cancellation. And so consider the function f of x equals x squared. Let's compute the derivative of this. The derivative of this is defined as being fx plus d, that's x plus d squared, minus f of x, in this case, that's going to be x squared, divided by d. So there's our formula. This has defined the derivative as d approaches zero, which of course is a huge problem with d in the denominator. So we'd like to simplify, progress here by expanding x plus d squared. So if you go back to your algebra, x plus d squared is x squared plus 2xd plus d squared. Hopefully that's natural. And you'll notice this x squared and this x squared are going to cancel. And so we can just get the 2xd plus d squared divided by d. Well, cool. We have a d in each of the terms left over now, and we can cancel them and just get 2x plus d. And the d is approaching zero, so in fact, 2x plus d is 2x. And if you remember your differentiation, the derivative of x squared is 2x. Hooray! Easy peasy. Differentiation is easy in that situation. However, we cannot always cancel. Suppose f of x is the sine of x. Once again, we plug this into the definition of our derivative formula. That becomes sine of x plus d minus the sine of x divided by d. And now we use our trigonometry knowledge that presumably we also have, which is that the sine of x plus d is the sine of x times the cosine of d plus the cosine of x times the sine of d. That's the angle sum formula. It's the greatest trigonometric formula ever, and you should definitely memorize it. And then, of course, we are still subtracting the sine of x and dividing by d. Okay, that's lovely. Now notice, as d gets really small, cosine of d, the cosine of 0 is 1. No problem. Excellent. That's fantastic. And that means that this sine x cosine d becomes sine x. Did I say that right? I think I did. Oh, but the thing is, this becomes sine x, and then it's canceled by the sine x over here. And that just leaves this cosine x sine d in the middle, divided by d, which looks like trouble. And then, so what we really need to know is find out what the sine of d divided by d is as d approaches 0. And that's why there's the big deal about finding the limit of the sine of d, or the sine of x over x, as d approaches 0, because that then enables us to figure out what the derivative of the sine of x and other trigonometric functions are, just with that one limit. That one limit is really valuable to have. And that's kind of the linchpin for almost all the other differentiation we do. For now, just know that the sine of d is d when d is small. And that makes it the case that the result here is just the cosine of x. And the derivative, as you may recall from memorization, the derivative of the sine of x is the cosine of x. And that's how we do differentiation. That's your basic 5-minute review.